Today we're going to finish off the radiation section, and I might actually do the fuller version of the cloud physics because we seem to be going quite well, so I'm confident that we're going to have time. So I might switch back to my slightly fuller version of the notes for the cloud physics, but let's see how we go. So we finished off last lecture talking about the consequences of the energy balance model, if you remember, and global warming. So what I want to do in this lecture is to briefly finish off talking about the actual... okay, I always forget. Do you know, I haven't had a phone for like months. I broke it. It fell in the sea, the last one. And I finally got a new phone last week, and I keep forgetting that I actually have one. Let's see if I can turn the thing off. I have no idea how it works. That's the problem. I can just about answer a phone call. There we go. I think that's off. No? Oh well, we'll see. Okay. I'm getting worse as the week goes on, no? You can tell it's a Friday. I think the projector's having a Friday day as well, no, by the looks of things. Hopefully it'll warm up in a moment. We'll see how it goes on. It's fading fast. This is not a good sign. Okay, so we're just going to finish off today talking about the just the radiative, should we say, actions of several commonly found gases in the atmosphere. So we can put the current discussion about increasing CO2 a little bit into context, into its role compared to other gases. Okay. So before we do that, I just wanted to remind us of the three components that we're going to very briefly discuss. I'm not going to have time to go into detail here. And that was the fact that as well as the thermal emission that we've already talked about, that we have an atmosphere of a certain temperature. It essentially is emitting radiation at a set of wavelengths according to its temperature. That we also have the possibility that radiation can be scattered. So a common object that we know that scatters solar radiation, of course, is like clouds. They appear very white. So that color, the whiteness, is because they're scattering sunlight from a different direction. They appear very bright. If we have a very overcast sky with very thick clouds, not many photons manage to pass through. Many are scattered back out to space, and so those clouds appear much darker. That color is an indication of how many photons are actually being scattered down towards us. Okay. So we have the direct solar component, the scattered component, and emission, as we said. Okay. So here I'm not going to go into much detail. I'm just going to give a very brief summary. So the first thing we should note is that for the solar wavelengths, so those short wavelengths, the thermal emission is unimportant. And we know this already because we've seen this from those Planck curves. So we know that at the temperature of the sun, that the vast majority of the radiation is emitted at the short wavelengths. And there's very little emission at the longer wavelengths. So we know that we can neglect thermal emission for the short wavelengths. Okay. On the other hand, for the thermal wavelengths, in general, scattering can be neglected. So for the thermal wavelengths, the important processes are absorption and emission. Okay. So we discussed black bodies as being bodies that are perfectly efficient emitters and absorbers. Okay. Gases are not like black bodies because, of course, they only are active at a certain set of wavelengths. So we already know this because I've kind of hinted towards this already. When we started to talk about grey bodies, we discussed the possibility that they could be grey in terms of absorbing 50% of the radiation across a range of wavelengths, or maybe they absorb all of the radiation at certain frequencies and certain wavelengths and let the other wavelengths basically pass through without any radiation interaction. So gases, in fact, are much closer. Their grayness is acting much closer towards this second model, as we saw. And I gave a hint of that at the end of yesterday's lecture already with that cartoon. Okay. And the reason why is the energy that a molecule possesses is essentially, as we already know, quantized. And we have basically three kinds of energy. We have electronic energy, vibrational energy, and rotational energy. So if we increase the temperature, for example, we're likely to increase the energy in the vibration modes, the kinetic modes of a molecule. And those, should we say, as we know, these energy levels are quantized. Okay. So if we have a molecule, I shall skip over that point, but if we have a molecule that has a certain energy level, okay, if it absorbs a photon, it can actually be excited to a higher energy state. Okay. And likewise, at a certain time after that event, it can then decay back down to lower energy state, emitting a photon. Okay. So for all of those different kinds of energy, kinetic energy, rotational energy, and so on, of electronic energy of a molecule, those energy levels are quantized. Okay. And the difference between these set spacing between these energy levels is directly, let's just bring up the text, is directly related to the wavelength of the photon that's emitted. Okay. So the energy difference between these states, like the vibrational states, is related directly to the frequency of the photon that's emitted. So what this means is that for a given molecule, say water vapor, that has a set, should we say, spacing of energy levels for example, vibrational energy, that we have a set number of frequencies of radiation that molecule can emit when it's changing energy states. Okay. So the more complicated a molecule is, the more different energy levels it tends to have, more different, should we say, vibrational and bending modes. So for example, I'm not going to go into detail here, but I think I mentioned it on the last, this is the point I was mentioning there. I have a cartoon in the full lectures. But if you have a linear molecule, like N2, then you tend to have just very simple modes that you can have. So you can, for example, here have a compression mode. Okay. Whereas a molecule like water vapor is already more complicated because it has a structure, H2O, so we have a structure that's essentially has a dipole. By what I mean is it's not a linear molecule. So you have a asymmetry between the positive and negative charges. So that means that you can also have more rotational modes. You can have flexing modes, for example, where the molecule can basically flex in this way. And then you've also got basically compression modes and so on. So the more complicated, just in simple terms, the more complicated a molecule is, and if it has a dipole between the charges, then the more complicated modes and energy levels you can have. Why is that important? Well, it's important because these energy modes determine both the frequencies of the radiation that you can emit, okay? Because if you have many different possible energy modes, you can have decay from here to here, here to here. I've drawn this badly because they're equally spaced. But you can also have changing over several levels. So the more, should we say, different energy levels, the more frequencies of radiation that you can emit. So I think I've pretty much discussed everything on that slide. Too much text on that slide, actually. So I've already discussed that. So what this means is that essentially, if this is a diagram here, actually, I was told to use the mouse yesterday, I think. If we have this cartoon here as represented on the x-axis, this is frequency, or it could be wavelength. Then essentially what it means is that you have possibility to have discrete frequencies or wavelengths where the changing of energy level means you can emit radiation at those discrete wavelengths, or likewise you can interact with photons with those wavelengths, because it's possible to absorb a photon with that energy and basically move up to a higher energy level for like a vibrational mode and so on. So what you would expect is that each molecule will have its own, should we say, radiative fingerprint, okay, due to its structure. So the different modes means that each one would have its own spectral fingerprint of a set of basically frequencies which it absorbs and emits radiation, and that's according to the structure of the molecule. Okay. So of course this is how, for example, remote sensing of the stars, they sense gases because they see the discrete fingerprint of the spectrum of the different wavelengths of radiation that are emitted, and you can use that then to say, oh, we know that this particular gas is present on that star due to its, should we say, emission spectrum. Okay. Now, in fact, we don't have what we expect to have, because we have these discrete energy, like quantized levels, is that you have precise emission exactly at this wavelength, and then at wavelengths close by, you have no interaction at all. But in fact, the absorption lines and the emissions tend to be spread out. They're kind of basically fuzzy. And there are basically three effects. One is the Heisenberg's uncertainty principle, although this tends to be quite a small effect. Another methodology for actually causing the spreading of these absorption lines is just simply due to interactions of molecules when they actually bump into and very close to other molecules. And so you get intermolecular basically interactions that distort the nature of the absorption. That's called pressure broadening. And another effect is simply a Doppler effect. So if you actually have motion towards or away from the observer, that can change, just like the sound of a siren of an ambulance when it comes past you. That can also shift the frequencies and the wavelengths. So you have a Doppler broadening effect. And so these three basically effects act to make these absorption lines not discrete at one discrete wavelength, but they broaden them over a range of wavelengths. So the top is a hypothetical, should we say, absorption spectrum, but these broadening mechanisms here mean that you actually have a spectrum of frequencies or wavelengths at which a gas is interacting with radiation, which are spread over these absorption bands. Okay? Mm-hmm.
If the gas is more complicated, a more complicated molecule, is the number of frequencies longer?
Yes, so you will have, because you have more energy levels, so you'll tend to have many more absorption bands. So when we go back to the diagram I showed at the end of yesterday's lecture, you will actually see that, for example, water vapor, being quite a complicated molecule, has a number of these, because it has a permanent dipole, especially this difference between the charge, the positive and negative charge, means that you have quite a number of bands compared to other simpler molecules, and molecules that have a linear structure, so you have no asymmetry in the charge. So, but before I move on to that, there's one other thing we need to mention, and that's the fact that what will actually determine the Okay, so what we're talking about. Yeah, so you could see this as, should we say, these are essentially absorption lines. or likewise emission lines, yes? Remember Kirchhoff's law, so you can view it in both ways. It's both absorption efficiency, but also emission efficiency. So this is often referred to as an absorption spectrum of a gas. Okay. So what this cartoon is showing is, again, we have frequency of radiation on the x-axis, okay? And this is absorption going from 0 to 1. So what this is basically a normalized absorption that's saying, given a certain, should we say, radiative flux, okay, at this frequency, how much of that flux is absorbed by a layer of gas. So let's imagine that we have a layer of gas, or it could even be a cloud if you like, but let's imagine we have a certain layer of gas. It's a little bit like that cartoon I've just shown you. And we have a vertical dimension of dz, okay? The gas has certain absorption properties. What would be the other, so apart from the thickness of the layer, what would be the other, should we say, characteristic of the gas that will affect how much of the radiation will be allowed through and how much will actually be absorbed? Yes, exactly. So, very good. The density as well. So, the density basically times the height anywhere will give us the total mass of gas. Now, if you imagine that we could have one of two situations, okay? If we have a gas that's maybe particularly efficient at absorbing at a certain frequency, or maybe we just have a particularly thick layer or a very high density, or maybe all three, we could have a situation where there's so much of the gas, or it's so dense, that none of the radiation at a given frequency passes through the layer. Okay, so essentially, all of the radiation at this central frequency, okay, nu0, is actually absorbed. Okay, and so we have this line broadening. So at a given distance, if we go far enough away from that central frequency, of course, eventually we have to drop back down to 0, because if you move far enough away from the frequency, you're going to be far enough away from that band that the broadening effect is no longer effective, and so you have no absorption, you see. So this is essentially the central part, if you imagine, of one of those absorption bands, but already enough in the middle, this is enough to absorb all of the radiation. So we end up with an absorption curve that looks like this, okay? On the other hand, so this is known as the strong limit, okay, and I'll explain this terminology in a moment why we say this. On the other hand, maybe we only have a very thin layer of the gas, or a low density, or maybe it's a particular frequency where it's not a particularly effective interaction. Maybe it's two energy levels that are very hard, because it's a very high energy level, so it's very hard to get it up, the photon, to that high energy level. So that particular frequency level is not at that energy level is not attained very often. It's very rare, which means that that gas, so that particular change between those two energy levels doesn't happen very often. So it's not a very effective emitter at that particular frequency here. That corresponds to a very rare energy transition. Okay. So in that case, maybe we have a situation where even at the center of the band, we're only absorbing maybe a small percentage, 10 or 20% of the energy at those wavelengths. Okay. And of course, we have this broadening effect, so as we move away from the central frequency, the absorption drops off. And that's called the weak limit. So what do we say is weak and strong limit? Well, what happens if we increase the amount of this gas? Okay. So we have a certain amount in the weak limit, and then maybe we double the amount, or we could double the thickness of the layer. Well, you can see in that case, we move to a situation where at all of the frequencies, both the central frequencies and further away, we're increasing the amount of the absorption. Okay. So the response in radiative terms is approximately linear. if we double the amount of gas, or we double its density, we tend to double its radiative effect. If it was absorbing 10% of the radiation at that frequency, or that frequency range before, that will be 20% afterwards. You can see that's not going to be the case for the strong limit. What happens then if we increase the quantity of the gas? Well, at the central range of frequencies here, you can see nothing's going to happen, no? Because we're already absorbing all of the radiation there. I remember now, actually, I think it's one of these. Just tell me if the, it's really, I think it's one of these plugs at the back. Tell me if it gets a little bit better. It's really, so I'll just give it a quick tweak. Is it changing anything? I seem to remember from last term it was one of these. No, I don't know. Okay, it was worth a try. It's really dark, no? Doesn't matter. Anyway, so these central frequencies here, increasing the gas doesn't make any difference, okay, because we're already absorbing all of the radiation. So where does it make a difference? Well, it's going to be at the edges of these bands, yes? So if we increase this gas, then the absorption here will increase because essentially we'll widen this. So it will go up here and here and here, and then here as well. So essentially we'll have an increase, okay? But that is called the strong limit. And the changes, if we double the, should we say, the quantity of the gas, you essentially get a logarithmic response, okay? And so this is quite important. So for example, carbon dioxide, for many of the absorption bands, we'll see in a moment, for many of the main bands, it's in the strong limit, which means if we double carbon dioxide, we're not doubling its radiative impact in terms of its absorption of long wavelengths. Okay, we'll see that in a moment. So, okay, a question then. Let's imagine now on this cartoon that we have, this is, for this given gas, we have a satellite that we want to design, okay? And we have a gas that's in the strong limit, okay? So this is my cartoon of the strong limit. Now, I've got a choice when I'm designing my satellite sensor of where to actually detect radiation, which frequency. So would I choose to detect here at A? Would I choose to detect here at B? Or would I choose to detect here at C if I want to detect the quantity of this particular gas that's in the strong limit? Where would I detect? Which frequency would I choose? Which one? A. Who thinks A? Okay, what about C? C, yeah? So why would you choose C? What's your reasoning for choosing C?
Because in this frequency we have maximum. It seems like maximum.
Okay, so here we have the maximum of absorption. And what happens if the amount of gas goes up? What happens to the absorption? Doesn't change, yeah. So if we have a certain amount, if this is the quantity of the gas, okay, I don't know, let's put M for the mass of the gas, okay? And this is the absorption that we're measuring. For a given initial quantity, we have an absorption of 1. If that changes, we have an absorption of 1. So can we tell how much gas we have? No, because we have no sensitivity, no? What about A? Well, A, we're a long way away outside the band. So I'm presuming there that if I increase the gas, okay, the band will change at the edges. Unless we have a really, really strong increase in the amount of gas, we're not really going to see very much, no? Because it's not until the band reaches here that we start to have an impact. So in that case, for many given masses of gas, we have no absorption whatsoever, and then eventually it starts to move up, yes? Whereas in B, we can see that decreasing or increasing moves this absorption up or down. So if I were to design a satellite and I wanted to detect this particular gas that's in the strong limit, then I would probably choose this point here, you see. However, I'd have to be a little bit careful because this is a simple example where I've just picked out a single gas with one band. But what we need to check, of course, is whether that also is a band at which other gases are also active. Because it may well be that this edge here for this particular gas is a nice frequency, it's very sensitive. But maybe there's another gas where this is right smack bang into the strong limit of another gas, which is absorbing all of the radiation at that frequency, because we have overlap, which we'll see in a moment. So that's another issue we have to take care of. This part of the cartoon on the right, by the way, is just to show that because we have these different shapes, often what we do when we want to talk about the strength of an absorption band is we kind of convert this absorption shape into just, should we say, a rectangle of one central absorption, and then we just basically can measure it by the thickness. So the area inside this rectangle is supposed to represent the area under this band, you see. And so if you want to give a number that measures the strength of this absorption band, we describe it in terms of the equivalent width of a band with height of 1. Okay. So I've already told you this, that carbon dioxide is in this strong limit, in fact. And we'll see this graphically in a moment. On the other hand, for example, CFCs, I don't know if some of you have heard of CFCs. They were used as I think a refrigerant in early refrigerators, and that they've been banned now due to the effect also on the ozone hole as well. But they were also particularly bad for their greenhouse effect because they absorb they have a weak absorbers, and they absorb in a part of the spectrum that other gases are not active. Okay, so we'll come back to that issue of overlap in a moment. Okay, so now we're back to this graph. I gave you a quick kind of sneak preview yesterday, a little bit like a movie trailer, no, at the cinema. Lots coming up next. So now we've gone through today's lecture, we can see that we understand much better now this picture. I'm just going to open this to let a little bit of air in, some of the chalk dust out. So as I said yesterday already, on the top panel here, except that when I showed it yesterday, this was colored red. Now the projector's dying, we lost the red color. So now it looks like a dark brown color. But this was essentially our hypothetical blackbody curve for the Earth's atmosphere at colder temperatures and the hot temperatures of the sun. And so now what this is showing us here is for this range of wavelengths or frequencies, it's showing us the percent of extinction in the atmosphere by either absorption but also scattering. I haven't talked about scattering in very much detail. Okay. So what we can see, and I pointed this out yesterday, is that in fact the combination of gases that are present in our atmosphere actually absorb 100% of a very wide range of frequencies in the infrared that are emitted from the Earth. Okay. Except for this range between around 8 and 13 microns, which is referred to as the atmospheric window. So we call it the atmospheric window because that's the only part where most of the frequencies pass through without being absorbed. And so it's a little bit like our windows here that allow visible wavelengths through them without any interaction in the glass. And so that's the window to space. And then what we have on the bottom of this this cartoon is the individual major contributions. I mean, this is not exhaustive, of course, this list, but these are the major contributions to this total absorption scattering. Okay, so in the infrared, let's concentrate on the infrared. This is all basically absorption, whereas in the short waves we have a scattering effect I'll come to in a moment. And so we can see that water vapor, because it has this charged dipole, and this comes back to the question, has a lot of different bands that overlap. And so you can see this very complicated spectrum with lots and lots of bands very close together. And so they all broaden. They basically merge into each other. They're a kind of smudge. And so you almost have at these very long wavelengths, look, you can see it's just a continuous absorption. And this is actually lots of these bands that are broadened, but they're so close together they basically join up. So it looks like a continuum absorption. Same thing here. And you can see this structure. You know, you can see evidence of these bands. These are weaker bands here in the middle of this window. Okay. Carbon dioxide, you can see, has a much simpler spectrum. Look, you can see that we have 1, 2, 3, 4, 5 major portions of frequencies where we have strong absorption. And then we have some more minor absorption bands. You can see here that there are 2 and here. But you can see that carbon dioxide, is it in the weak or the strong limit? We can see straight away here, no, that it's in the strong limit. Because at the center of these bands, we have 100% absorption. So that tells us that if we increase carbon dioxide, we double it, we're not going to double its radiative impact, because in the center of these bands, it's not going to make a difference. All the more so, and this comes back to the other issue I already mentioned, because we also have overlap between the gases. So, for example, if we look at this left-hand band here, even if this were not in the strong limit, and it was only, for example, halfway up, you can see that there's essentially also a strong water vapor band there. And so the total is anyway 100% at those frequencies, you see, due to the fact that you have overlap with the water vapor molecule. Whereas you can see, for example, methane here, even though its overall radiative impact is much smaller, if you look at the area under these curves, its actual radiative impact in terms of watts per meter squared, the amount of energy it's absorbing, is less, much less than carbon dioxide and water vapor. However, it's quite important because if you look at this one here, for example, it's kind of smack bang in the window. There it is. You can see it popping up there. Okay. So it's important because its response is linear. If we double the amount of methane, okay, we're going to double the radiative impact here. This band will get bigger, and we're right pop bang in the middle of the window. Okay. So if we're designing a satellite to measure methane, in fact here, either B or C would work quite nicely, I presume, because if we take a frequency here in the middle, because it's not saturated, it will be sensitive to the amount of methane. Okay. So I think that illustrates now, I think now we've gone through that, at least in a very, should we say, brief overview, we understand much better now this picture. More briefly, if we look at the solar spectrum, we can see 2 major components, okay, well, in fact, 3. We have, on basically the far infrared, this portion of the spectrum here, we can see that water vapor is active. So if you remember, I mentioned that there is absorption of the solar radiation, that assuming that solar radiation doesn't interact with the atmosphere was a fairly rough approximation. And that water vapor, particularly, for example, in the tropics where we have warm temperatures and there's lots of water vapor, can absorb, you know, a good percentage. It depends on where you are. Water vapor, even in the tropics, changes very greatly from location to location, very rapidly, from like 20 to 50 kilograms per meter squared very quickly. So you can have a big impact of, well, should we say, changing the absorption in these bands here. Ozone in the stratosphere, remember, I already mentioned that the warming in the stratosphere was partly due to the presence of ozone, and that's absorbing here in these wavelengths. So ozone is protecting us because it's absorbing at these very short wavelengths. Okay, and these are very dangerous to our skins and so on. The ozone hole is dangerous because of the fact that it's letting these very, should we say, short wavelengths through to the Earth that we're not basically equipped to deal with. And there's also a component due to Rayleigh scattering. I'm not going to talk about this in detail in this course, but this is a scattering effect. Okay, that's very frequency dependent, which is why we have like the blue sky and we see the sun as being red. It's a different amount of scattering at different wavelengths. Okay.
We have told that the carbon dioxide is one of the most important reasons for the global warming.
The say again? Say?
It is one of the most important elements for the global warming.
CO2. Yes. Yes.
But here, it doesn't look like that important.
Okay, I mean, that's a good question. So probably what makes you think that is the fact that the water vapor is a much stronger greenhouse gas. Yes. The big difference between the two is the life cycle and the timescales of the two, and the fact that water vapor, as we'll see in the cloud physics, has this kind of natural limit. So if you do something to increase water vapor, if it goes above that saturation limit, then it's just converted into rain and it falls out. Okay. Carbon dioxide has very long timescales once we emit it. Even if we were to cut back our emissions now, essentially it has very long lifetime in the atmosphere. Okay. And so it's more important because it's, should we say, a driver. What we do, we don't actually change our actions directly, water vapor. If we were to try and, should we say, increase the water vapor, it would just rain out because it's controlled by the temperature itself. Indirectly, and I should talk about this just in a couple of slides' time, indirectly, water vapor is important because if you imagine that we increase carbon dioxide, okay, even though it's in the strong limits, it does. Would this happen yesterday as well, Adrian? You can tell I'm not very good technically. I always, it's like, this is a disaster. I'm always crashing my programs. There are, should we say, parts of the spectrum. For example, if you look at this band here, we can see it here. So even though it's in the strong limit, if we increase the amount of CO2, it will increase this emissivity. So doubling CO2 is, should we say, has an impact of around 4 watts per meter squared integrated across all of these wavelengths, okay? Now, increasing the radiative forcing just by CO2, 4 watts per meter squared, on its own would have an impact. If you plug it into a simple energy balance model, you can do that tonight if you like. You could make just a small adjustment to the emissivity value, okay? See what happens to the surface temperature. And just on its own, it would have an impact of just over like 1 degree, 1.2 degrees. Okay. But the point is, and I should talk about some other examples, is that there are all sorts of ways in which that signal can be either amplified or reduced, so-called feedbacks. So if we look at this straight away, we can see one of the feedbacks is if we warm the atmosphere, we increase the water vapor, exactly, because we increase the saturation limits. Remember that we talked about on the board on Monday. And so the water vapor can remain in the atmosphere before it's converted to rain. And so if we have more water vapor in the atmosphere, then we also start to increase absorption across all of these. Okay. So the water vapor is a major positive feedback in most climate models. One of the reasons why, if you look at the probability density function of all the different models, the predictions, they just about all of them have a warming that's larger than 1.2 degrees. And that's due to the amplification, among other causes, but one of the most major amplifications is the role of water vapor.
Okay. Would there also be a negative feedback in that the water vapor goes into the formation of clouds?
Yes, very, very good. So clouds can also have feedback, but they have ways in which they can both amplify and decrease. Okay, I'm going to talk a little bit about that just in a moment. We'll start to think about the radiative impacts of clouds. So bear with me just a moment on that one, but it's a very good point. I mean, clouds can both amplify and decrease. And in fact, clouds are the most uncertain, one of the most uncertain components of the climate models. And we'll see why in next week's lectures, because it's one of my actual kind of main areas of expertise, actually, is the representation of these clouds inside the weather and climate models. And so I'm going to give just one simple example of how we represent them, and you'll see the level of uncertainty. Is I really don't hear you if you don't speak up. I'm sorry. Yes, I mean, that comes back to the point I already made, the fact that why do you think that we say, when you read in the journals, they say methane is a more efficient greenhouse gas? Why do we think that often in the newspapers, if you read about global warming, they say, oh, methane is even more important than carbon dioxide? What do they actually mean when they use that language? They say it's a more efficient greenhouse gas. Now, which is the terminology I just described for the? I said there's two weak limits. So which one is methane in? Ooh. Weak, yeah. Because remember, the strong limit is when we are absorbing all of the radiation in the band. So it's a little bit, the terminology sounds the reverse. You say it's a very effective greenhouse gas. You think, well, it's in the strong limit because it's strong. You know, it's strong. It's got a bigger. No, it's in the weak limit. So that's why it's an effective greenhouse gas, because it's in the weak limit, and therefore we still have a lot of potential to increase its absorption signal. Okay. However, it doesn't mean that it is causing more warming in today's climate than carbon dioxide. You can see that very clearly from here. Look at the areas underneath these bands for carbon dioxide and compare them to methane. The actual present day warming caused by carbon dioxide greatly exceeds methane. But when people refer in the media to methane being a more effective greenhouse gas, they simply mean that it's in the weak limit, and therefore if you double methane, you double its greenhouse effect to a certain degree. Take into account, of course, the fact that some of these bands overlap others. So it's a little bit less than that always. And on the other hand, carbon dioxide is in the strong limit, so it has a logarithmic impact. Okay. However, if you greatly increase carbon dioxide and you only increase methane by a small amount, or if you double methane, it doesn't necessarily mean that doubling methane will have the same impact as doubling carbon dioxide, because carbon dioxide has more bands, you see. So you have to take into account the thickness of the layer, the density, and so on, the amount that you're changing the gas by. So all they mean when they say it's more effective is what they mean is now you can say, that means it's in the weak limit. Okay. So if you take into account both the absorption and the scattering effect, in fact, in total, it adds up to around 17% on that shortwave that's actually either scattered or absorbed compared to the black body. So now I have a few cloud related. We haven't talked about the cloud physics yet, so I'm just going to talk about the actual radiative signal of the clouds. Okay. Now, clouds are quite complicated because clouds actually are active both in the shortwave and the infrared. So clouds are very effective black bodies in the infrared. Okay, so they're very, unless a cloud is very optically thin. So an example often is on some of these very, should we say, nice sunny days. If you look closely, sometimes you can have still a very thin, wispy, high-level ice cloud of cirrus. Okay, so we still have a lot of sunshine. It's a nice warm day, but you can see this thin, wispy cirrus. That's an optically thin layer. So it's an optically, should we say, thin cloud. I haven't gone into the mathematics here. If you do the full class, I go through the definitions of optical depth and so on. But essentially, the majority of the sunlight is passing through. And that's simply because that layer of ice cloud is very thin. Its geometrical thickness is thin, and it doesn't have a high density. Okay. If you have a very thick ice cloud, so when we have like thunderstorms, you get this. I think I had an example right on the front page of the notes. I had that photograph. So when you have these thunderstorms, and again I talk about these in more detail in the full course that I do in the diploma. So you have these thunderstorms, and you have this strong what's called an anvil cloud, when the thunderstorm is developing and you have this large outflow from the main updraft. I'm sure you've all had a chance to look at a thunderstorm develop in the distance on the horizon. They're really beautiful objects. And so these, again, are ice clouds, but they have a bigger dimension, and the density is much higher. So then all of the sunlight is extinguished. You see, you don't see through the cloud. So we say they have a large optical depth. So clouds are black bodies in the infrared, but they're very effective scatterers of shortwave radiation. So when they're, like I said, if a cloud like the wispy cirrus is very thin, then it's not scattering much light. Most of the sunlight gets through, but also they're not absorbing all of the infrared radiation. But as soon as they reach a reasonable thickness, they act as black bodies and they extinguish a lot of the sunlight. But it's very complicated because clouds can consist of water droplets. The water droplets can have different sizes. We'll talk about this on Monday's lecture a little bit more. And also, once you reach cold temperatures, those droplets can freeze, okay? Or you can form a cloud directly in the ice face, okay, where you form basically haze particles which immediately freeze. And the ice crystals make life even more complicated because they can have all sorts of different shapes. You can have needles, you can have basically hexagonal basically plates. You have this you can have hexagonal plates that are basically, I'm a terrible artist, but they're joined on the end of these needles. You can have these dendrites, you can have the pure, pristine snowflakes that have this kind of, how do you say, symmetry, the kind of, but then they can become interlocked together, so you get a very random aggregate of many of these crystals joined together where the arms get entangled. And so this has a big impact on the scattering properties of the crystal when it interacts with sunlight. Okay. How much sunlight, if you have a photon arriving from a certain direction, or many photons, how many are scattered in the forward direction and the backwards direction, and so on. Okay. So the optical properties of a cloud are very much dependent on how that cloud is made up. Is it ice? Is it liquid droplets? What are the shape of those ice crystals? But also where it's situated in height. So all I'm going to do here is just get us to think a little bit about this, especially this aspect of the height of the cloud. Why do you... Yes, I mean, you have essentially cloud chambers. And cloud chambers are essentially large vats where you're able to drop the pressure very quickly and form cloud droplets through the change in pressure. Okay, but I will leave the discussion of that until Monday because now I want to start talking about the way that droplets form. So if I start talking about that now, I think that will just confuse things. But so cloud droplet formation is the subject of Monday's lecture. So I'll come back to that on Monday. Okay, where was I? What was I talking about before? Sorry. Oh, height. Yeah, that's what it was. Height. So the question, yeah, thanks a lot. The question was, why do you think height will be an issue for the radiative properties of a cloud? It's not, for me, it's not an obvious question straight off. I mean, if you haven't thought about it before. So I've talked about the fact that, if we change the shape of the ice crystals, it will change the way that light is scattered. Well, that seems fairly obvious to understand. It's a very complicated thing to model, but to understand. But why do you think the height of a cloud will be important for its radiative impact? Seems strange, no? If we take a certain cloud, has certain properties, why do we care where we move it? I mean, it could be here, it could be at 5 kilometers, 10 kilometers. Let's just assume for the moment that even if we move it to 10 kilometers, it's still a liquid cloud. Okay, forget about the ice changes. But just a cloud with a certain optical property, but we move it up or down in the atmosphere. Why is that going to be important for its radiative impact? What do you think?
Yeah, like the graph we saw yesterday, the absorption or emittance is a function of temperature. Yet, we know that temperature keeps on reducing as we go upwards.
Exactly.
So, the position of the cloud.
Exactly. Very good. So if we move the cloud up, it has a colder temperature because the cloud more or less will be in equilibrium with its environment. So in very fast updraft motions, so in the deep thunderstorms, the air is moving up very quickly. So it's not quite in equilibrium with its surroundings. If you fly an aircraft, and people did do this, after the Second World War, there was a surplus of aircraft which were quite robust, and there was a surplus of pilots. And so that was when research into cloud microphysics really took off in the late 1940s. They said, well, why don't we have all these aircraft? We haven't got anything to do with them. So they fitted them up with devices to try and measure both temperature, humidity, and cloud droplet densities. And then they got some crazy pilots to just fly straight through the middle of the thunderstorms. You know, when you're on a commercial aircraft, you often go around these things because it's pretty bumpy. You know, these updrafts can be going at 10, 20, even over land, they can even reach 30 meters per second. So, you know, it's a pretty bumpy ride. But if you do that in those fast updrafts, because they haven't got time to reach an equilibrium with the surroundings, you can measure temperature perturbations of 1 at the very outside, maybe 2 or 3 degrees difference between the inside of the cloud and the outside. Okay, because you've got the warming due to the condensation, and you have a fast motion. But normally a cloud that's not undergoing very fast turbulent motions will be more or less at the same temperature as its surroundings. So as we go up through the atmosphere, remember we have that strong drop-off with height. And so you're very correct to say that the sigma t to the 4th tells us that the infrared emission, okay, will be very different at cold temperatures compared to warm temperatures. So let's have a little think about the balance again. And this is not obvious at all. So, okay. So I've already talked about this, about the ice crystals. So I keep running ahead of myself here. Okay, and clouds are complicated. I've already told you this as well. Okay, so let's think about the effect of clouds. So the first example we're going to think about is a low cloud. Okay, so what I mean is a cloud that's probably within 1 or 2 kilometers of the surface. Okay, so we can assume that the temperature is fairly close to that of the surface. It may be a few degrees, 5, 10 degrees cooler, but on the grand scale of things, it's fairly close to the temperature that the surface has. Okay. So let's think about the two radiative, should we say, blocks of wavelengths in turn. First of all, the short wave. So I mean basically all of those wavelengths under the black body curve of the sun. Okay? And then the long wave. So in the short wave, if we have clouds of a sufficient optical depth, okay, they are very effective scatterers, and they will reflect sunlight back towards space. Some of the scattered light carries on in the downward direction, but some of it gets scattered back to space. So if you ever, when you look down from an aircraft and you're above the clouds, you'll see they're always extremely bright to look at. It's like looking at a snowy surface, and that's because they can have albedos that basically asymptote to about 70%. So, 2/3 of the light that basically arrives at the cloud is reflected back out towards space. So they appear very bright and white. It's like basically looking at a snowy surface. Okay. So if they're reflecting all this light back out towards space, they reduce the amount of light that reaches the surface. And we know this. If we have low clouds, we generally have lower afternoon temperatures than we would have with a clear blue sky day. We know that when the cloud goes over and it's hot, it makes us feel much cooler immediately. It reduces the incoming solar radiation. So the signal, in terms of the impact at the surface, will be a cooling, yes? Okay. Because we're increasing the albedo. What about the long wave effect? So we have a low cloud. Let's draw a cartoon again. So this is the surface. okay? And this is height, okay, and we'll say going up to 10 kilometers. So we're looking at the radiative properties of a low cloud. So its temperature is quite close to that of the surface, okay? So what will be the radiative impact? Well, if I ask that question, I'm not being very fair, because if I say, what's the radiative impact, I should really ask you for a certain position. Because remember, when we did our simple model, we talked about the radiative balance at different locations, yes? We worked it out for basically the top of the atmosphere, or for the actual, should we say, layer of the atmosphere, or at the surface. So let's imagine now that we're sitting here and we're measuring from a satellite into space, and we're looking down, in fact, and we want to look at the amount of energy that's emitted to space. Will this cloud have a large impact on the infrared budget if we're looking here, or we're looking at, should we say, just bare land with no cloud above? Well, let's think first of all, will it reduce or increase or not change the amount of outgoing long wave radiation, do we think? Will it reduce or increase? It reduces. Why do you think it reduces? It's the right answer, so have confidence. But why do you think it reduces? So imagine we have if we look at the land here, and we have a certain temperature Ts, and then we have a cloud temperature here. Is that cloud temperature lower or higher in general than the surface? It's lower, yes. So if we're looking down, and this is a black body, all of the radiation that's emitted from the infrared is absorbed by the cloud, okay? And then the cloud is a black body, you know, so it has an epsilon value of 1. So it's a little bit like our energy balance problem we had before, where we just treated the whole slab atmosphere. It's just that now it's one small block, but it's a black body. And so it's emitting temperature both upwards and downwards, okay? So we already saw having the atmosphere, even with an epsilon of 0.6, warmed the underlying surface in the infrared because it was emitting upwards and downwards. Now with the black body, that effect will be even larger in the infrared because the temperature is slightly lower, the temperature is lower, like for the atmosphere, but also we have a black body, so epsilon is 1, so that makes the effect even stronger than for the atmosphere. So you're right to say that the radiation emitted will be reduced, okay, compared to a surface with the atmosphere above, because don't forget we still have the atmosphere here as well. But if we take, for example, a high cloud, now this is a black body, but it's at a very cold temperature, okay. So this is absorbing all of the infrared radiation from the atmosphere block below, plus it's absorbing the atmosphere from the surface that's passed through the atmosphere here and arrives at the cloud. And then it's emitting to space at a much colder temperature. So this will tend to reduce the outgoing long wave radiation, but by a small amount, okay? Because at the end of the day, you've still got all of this atmosphere above with unchanged properties, and this is just slightly colder than the surface. So we'll have a small impact. This will have a very large impact at the top of the atmosphere, okay? So, and again, we have that experience. For example, in Trieste, you've passed the winter now, and you'll probably notice that on winter nights where we have an overcast sky, well, you tell me, when we have an overcast sky, is it warmer at night, or is it warmer at night when we have a clear sky? Overcast, exactly. Because we have the cloud layer, and at night, we don't have any absorption of solar radiation. So, the sun is below the horizon, so we only have the infrared to consider. And in winter, if we have clear skies, especially in winter, because in winter it's very cold, so what does that mean about the epsilon value of the atmosphere, do we think? If it's very cold, what would that do? Do we tend to have lower or higher emissivity values if it's very cold? What do you think? Hmm?
We want a waiter because it's cold and it can absorb
Well, let's have a think then. So if it's much colder in the winter, who thinks that emissivity will go down and why? So if it gets colder, what does that change? So the temperature's going down, so what is it? Yeah, because when it's cold, we tend to have much less water vapor in the atmosphere, remember? And therefore, we have a lower emissivity. And so what that means is in the winter, if we don't have much water vapor, the atmosphere loses with a low, if it's very dry, especially here on the plateau. We have like often northwest winds, the Bora winds, they're very, very dry. The relative humidity is very low. If the relative humidity is very low, there's not much water vapor. We have a low emissivity, which means that the emission from the ground, nearly all of that radiation can just go straight out of space. Okay, so it cools very effectively. So if you have clear skies and low temperatures anyway of the atmosphere and not much water vapor, because we have dry winds coming from the mountains, then the temperatures can just drop and drop and drop. It's the same thing over the Siberia. When you have the high pressure over Siberia, high pressure, the air is going down, so it's very, very dry. Because it's dry, each night it just gets colder and colder and colder. You get this cyclic effect. Add some cloud in, and the picture changes, of course. Because now, if we have this cloud, what happens? The emission, bam, straight into the cloud, black body, absorbs all the radiation, and it's basically quite low, so it has a fairly warm temperature, and it's emitting back down. So it's almost acting like an insulation blanket. And so it makes a big difference in the winter. You'll see a big difference between the nighttime minimum temperatures if you have clouds or clear sky. And this is the reason. You see, now we're starting to appreciate how this meteorology is actually working. Bene. So we've discussed this. Okay. So high clouds will have different properties in the short wave because we have ice crystals rather than water droplets, so it does change the scattering properties, but they will be effective scatterers. But in terms of the infrared budget of the whole Earth atmosphere system, as we said already, they will have a much stronger infrared impact. Okay. So in the tropics, in fact, if you're looking at the budget of the solar and the infrared radiation at the top of the atmosphere interface in the tropics, it's quite surprising that, in fact, the infrared and the short wave impacts of clouds almost exactly balances out. Okay. So the reduction in the solar radiation that basically passes through the clouds, so they increase the albedo, that effect on the shortwave radiation through the scattering and the reduction in the solar radiation that's absorbed is almost completely offset by the impact on the infrared budget, okay, at this interface. So when I say solar radiation that's absorbed, of course, I mean solar radiation that can pass, through the clouds, is scattered in the forward direction, and is absorbed by the surface. Okay. Take into account, of course, that there's another 10% that's absorbed by water vapor in the atmosphere. We saw those bands. So this is what I mentioned at the bottom of this slide, that this infrared and shortwave impact in the tropics actually almost exactly cancels out. In fact, there's a Professor Hartman in Seattle that actually has a theory that I think is quite nice, that he's suggested for an actual mechanism that should actually happen. It's like a constraint rather than just a coincidence. But I won't talk about that today. So what I'm going to do now is, actually I'll move straight on to the figure. where we look at the radiative forcing of the short wave and the long wave. Okay, and I apologize for this figure. I need to make these numbers larger on the right-hand side. Now, unfortunately, we've completely lost. This is not good at all. On the video, it will come out, hopefully, because it takes it straight from the computer. But the colors, as you can see here, are completely different. They're actually green rather than yellow. So you're going to have to bear with me. But basically, these blues are essentially negative values. And then these yellows here are corresponding to greens. Okay. And then we have these oranges here into reds. They're fairly similar. So I think what we've lost is one of the colors here. And so one of these panels, and I haven't labeled them, but one of these panels is representing shortwave, and one of them is representing the long wave impact of clouds. And this is the net impact of clouds, okay, on the top of the atmosphere radiation budget. Now, we haven't gone into detail about the distribution of clouds, but for example, if I tell you that off the west coast of South America, this is a location where you tend to have a lot of stratocumulus low cloud, okay? And off the west coast of Africa here is another location where we tend to have a lot of low cloud at 2 kilometers. Now, if I tell you that, which, and I'm apologizing for the projection, but maybe you can still tell me, which of these is the short wave top of the atmosphere impact of clouds, and which of them is the long wave, do you think? Oh yeah, some of you have the printout there. So we can see that this graph here has a couple of contour lines and a couple of contour lines here. So there's quite a big impact here, whereas this graph is showing no impact in these regions. And these are regions with low clouds. So here we have no impact, and here we have a big impact. So which one of these is short wave, and which one is long wave from these two panels, do you think? So low clouds, do they have a big impact in the infrared? What did we say? No, because they have a temperature that's very similar to the surface, remember? So if the low clouds are present here, and we look at this graph and we see that there's no contour line there at all, there's not really a big impact of the clouds, just a very small one. Whereas here we have like basically a big local impact due to low clouds, which is reflected here, you see. And we know that this must be the shortwave component, because the low clouds are very shiny, they reflect sunlight back to space. They change the top of the atmosphere shortwave budget. But because those clouds are low, they don't have much impact on the long wave. So we have a very small impact. Small impact in the infrared, large impact in the short wave, results in a net impact here that's quite large, you see. And this is just dominated by the short wave impact. If we look here, along, this is 0 degrees, this is the equator, okay? And so this is the western Pacific warm pole, where we have warm temperatures at the sea surface. And then this is all the way along the equator, and we can see another band here, north of the equator across the Atlantic. There's a sampling issue here. We don't have much sampling, so it's just colored white. But you can see here that we have this band here across the Congo and the equatorial part of Africa, and then the Indian Ocean. So these are clouds. Do you think these are high clouds or low clouds? These are across all the warmest parts of the tropics. These are going to be high convective thunderstorms, yes? So this is what's known as the intertropical convergence zone, where we have essentially air converging along close to the equator, not on the equator, and essentially then we have deep thunderstorms where the air is rising up to the tropopause. Okay. So these are deep clouds, high clouds, and we can see that they have a strong impact in the infrared. You can see these dark colours here. So they have a strong impact in infrared because they're very cold, but they're also very shiny in the short wave. They reflect a lot of sunlight back out to space. And so we have a strong impact here, and we have a strong impact here, which is easier to see on your printouts. And if you look, the infrared plus the short wave almost exactly cancels, look. So we have no impact at all in the net on the top of the atmosphere. So the net effect of the low clouds and the high clouds is really, when you look at the net radiative impact, you only see where the low clouds are, okay, and not the high clouds. I'm going to find them.
Okay, I can't remember quite well, but when we were doing the El Nino phenomenon with Fred,
Yes.
there's something he told us, though I can't remember, to ask you about the West and the East Pacific. I don't know in terms of it's something.
Was it about the type of cloud that you get? I actually had in my full diploma. I actually do have a simple cartoon of the circulation across the Pacific. So if you're interested, I can just take a few minutes out actually to just try and explain that. But if you imagine this is a section going across the Pacific, okay, east to west approximately, this is just a rough cartoon of, probably he was talking about the Walker circulation in the Pacific. And so in the western side, you have what's called the Western Pacific warm pool, where the temperatures are essentially on the order of around 300 to even 303 Kelvin. So the sea surface temperature here is around 27 to 30 degrees C, okay? And then it drops off into the 20s when you get to the colder water that's near the west coast of the Americas. And this is colder because you have there like an ocean circulation off the west coasts, where you tend to have upwelling of water that's from very deep levels that rises to the surface. And so that's known off the Americas as the Humboldt current. And that's bringing cold waters to the surface, which is actually very good for fisheries because it brings lots of nutrients up to the surface as well. Okay, so you have colder temperatures here, like in the low 20s. And so the warmer temperatures here is a little bit like we were talking about before. You have warmer air, you have like a lower density. I haven't gone through the basics of thermodynamics, I know. And the warm air tends to rise. So you get deep thunderstorms here over the Western Pacific. And you can get them also over the Eastern Pacific, but they happen much less often. It's much less frequently because you have lower temperatures here on the whole. What goes up must come down, so you have basically compensating subsidence, but the compensating substance spreads out over a very wide radius of deformation very quickly. Okay, and the reason why is a little bit like an analogy. Okay, so imagine you have a pond, a lake, okay, and I want to throw in a stone or a rock, and I throw it into the lake. And the rock has a volume. What happens to the level of the lake when I throw a rock into the lake? Does it go up or down? It goes up, yeah? Archimedes, displacement. Does it go up everywhere instantaneously? No, because when I first throw the rock in, of course, the other side of the lake doesn't know about the rock yet. It has to be communicated. How is it communicated? By gravity waves, ripples, exactly. So when you throw the rock in, immediately the level around goes up, okay? But then due to gravity, it's like an unstable situation because the water's higher here than it is here. So it wants to basically move down, and so you get oscillations and ripples. And that's those wave packets known as gravity waves spread out. Inside those waves, the level of the lake is slightly higher. And outside, the lake doesn't know about the rock yet. And eventually, they spread all the way out. And the lake afterwards is infinitesimally higher to account for the rock. It's just like this in the atmosphere, upside down with the convection storm. The air moves up, and it has to move down. And it spreads out by gravity waves. Okay. In the mid-latitudes, the spread is constrained by the fact that we have rotation of the Earth, okay, the Coriolis effect. But on the equator, because you're on the equator, so you're rotating like this, the Coriolis effect is essentially negligible. And so these ripples can spread out almost indefinitely until they're just dissipated by friction. Okay, so you have a much wider, what's known as a radius of deformation. So you have substance spread over a very wide area. And so the air is going down here. And so what tends to happen is this air is making the air very stable and warm, and it actually acts as a kind of cap on convection. So you'll have trade cumulus, and eventually moving right down to basically stratocumulus clouds here. And so this air above is moving downwards, and as it moves downwards, it's retaining its moisture, so that here it's cold, very low humidity. The air moves down. It just conserves its humidity. So the actual humidity is the same, but the relative humidity, because this air is much warmer, as it descends, it warms. It means that the relative humidity here is very low. And so you have this kind of capping inversion. And so you get this kind of cross-section of the clouds across the Pacific. That's why you get these deep clouds here, then trades of like, say, 2 to 3 kilometers in depth, and then these stratocumulus clouds in the eastern Pacific over the colder temperatures, with this direct circulation like this, which is known as the Walker circulation. Okay. I think that's as much I'm going to talk about this now. If any of you are doing the full diploma next year, I talk a little bit more about the cloud physics and the thermodynamics in more detail. So that's why you kind of get these cold, these low clouds over the cold temperatures here off these area. So now when you see a graph like this, this is from the IPCC report, okay, I'm hoping compared to Monday that it's a little bit clearer, this kind of diagram, because now we really understand some of the, at least some of the basic idea of the physics that goes into these balances, okay. We can see that we have 342 watts per meter squared an incoming solar radiation, and now you know where that number comes from. Yeah, this is S0 divided by 4. Okay, so you'll see that and you go, oh yeah, that's S0 divided by 4. Okay, and you'll say, well, hang on a second, I seem to remember 240 watts per meter squared. Oh, that was 1 minus alpha, the albedo. Well, here it is. Okay, so 342, and then we look at the IPCC report cartoon, and here's 107. You think, well, that sounds about right to me. That's that alpha, 0.3, remember? So 0.3 times 342 is pretty much 107. So a fairly good approximation. So we think, I know where that number comes from. Now we understand. And here we have that broken up into kind of 2 components. Okay, reflection from the surface, which can be very different according to the underlying surface. It will be very different if we have snow, or if we have trees, of course, or if we have ocean. And then we have basically reflection by aerosols, atmospheric gases, and clouds. And we say, oh yeah, we know that clouds are very shiny, very reflective. And in fact, probably we think that most of this is clouds. And if you thought that, you would be correct. Okay. Here's a little arrow on the right, absorbed by atmosphere, 67. That's not much compared to 342. Now you say, I know what that is. That's all those water vapor bands in the far infrared. Remember that curve? That's what that 67 is. I know that, and that depends on the amount of water vapor. And I know that that number, you know now, looking at that, you know it's going to change if you're in the tropics or the mid-latitudes, because it changes with the amount of water vapor. You see? And I've pressed something again. So, honestly, we can tell it's almost the weekend. No? It's like, and then we can see that from the 342, then we have 168 absorbed by the surface. On the right-hand side, to recap now, we understand this much better. Okay, so we have this emission from the surface. So 350. Okay, and then we've got this, and I don't like this term at all, back radiation, okay, because we have gases in the atmosphere, and we have emission from the atmosphere and the clouds towards the surface. I don't like this name, back radiation, because it implies almost like the radiation's been reflected back, like it's the same photons that somehow have been reflected back. I think it's a little bit misleading, because you have to remember with the infrared that the atmosphere is absorbing the radiation, the energy state has been excited, and then at some future time we have decay and emission of a photon. So it's not the same radiation, it's different from scattering. So when you're going through these notes and trying to understand, one important concept is not to mix up scattering with absorption and emission. Okay, make sure you have your language very clear for that, for the distinction, because I often find students start to say, yeah, the infrared radiation, it's kind of absorbed by the clouds and then scattered back to the surface. It's not. Be careful. Make sure you have your language very, very clear. So have this picture in your mind of the infrared radiation being absorbed, those energy levels being basically moved to a higher energy level, and then at some time later you can have decay. Maybe you don't have decay to that previous level, maybe you even go to a lower level or to an intermediate level, you see. So remember, and that then should line up in your mind with those different spectral bands. So we can see that there's a very thin line here, which is basically 40, and it says atmospheric window. And now you know what that is. That atmospheric window is that place between, can you remember the wavelengths? 1813, good. Okay, I'm not going to expect you ever to remember numbers like that. That's what books are for, but it's just to kind of see if it has any way registered. So, and then we have a component that's emitted by the atmosphere, and we can see this quite large, yeah? It's like around 165. And we know that this order of magnitude of this value is related to the emissivity, remember? Because the atmosphere is which kind of body? It's a grey body, remember? So we have grey body emission, and this basically adds to the black body emission by clouds and the amount of the component that passes through that 8 to 13 micron window, and they add up to an outgoing radiation of 235. Okay, well, 235 doesn't balance 342. Why not? Shouldn't they be the same? Because of reflection. That's right, exactly. So this minus this is the net incoming solar radiation. S0 divided by 4 times 1 minus alpha p. And this is balancing our outgoing long wave radiation that has simply one component from the atmosphere and one component from the surface. Okay, so you can see in this rather complicated looking diagram already those components of our energy balance model, you see, and we can understand where those come from. Now there's two arrows here that I haven't talked about much in this course. I have talked about it a little bit in passing. So we just mention those just to kind of finish off a little bit here. And that's basically this, I think, again, a rather poor name. It's, I refer to this as the sensible heat flux. It's like a conduction and evapotranspiration. So this is a flux of energy associated with evaporation from the Earth's surface or evapotranspiration from plants. Okay, so phase change. And this is another heat loss, and this just comes back to what we were saying about before, that we don't have a radiative equilibrium in the atmosphere because we also have motions. So we have heat that's like passed to the atmosphere by conduction. So a little bit like if we have a radiator in the room, how does that heat the room? Well, the radiator is emitting thermal radiation, but it's essentially heating most of the room by convection and movements of currents, because the air that's close to the radiator is heated by conduction, but then it's warmer, so it's lighter, so it rises, and the other air sinks, and so we have a circulation in our room that's driven by the warm currents. Okay, so it's a little bit like this in the atmosphere. The air is basically warmed, and then it can rise. Remember I talked about those stability. I know I didn't go into that in much detail because that requires more time, but just to emphasize that we don't just have a pure radiative balance. Okay. Okay, I've still got 2 minutes, so if you bear with me, I know it's almost the weekend, but I will just talk a little bit about some of these just to kind of use the time as much as I can so I can try and start on the microphysics as early as I can on Monday to make sure we keep on time. We've talked about this long-term balance, but we've already mentioned that we're actually impacting some of these gases. Yeah? So, and one of those is the fact that by burning fossil fuels, we're increasing the amount of carbon dioxide in the atmosphere. So these, again, these are IPCC plots. And this is time before the present, going backwards here. And these, should we say, from different records. So, for example, also ice cores and so on, reconstructions of past concentrations of, for example, this is carbon dioxide, and then this is methane, and this is nitrous oxide, I think. So we've talked about the radiative impact of carbon dioxide and methane, and this little window here, I think, is a blow-up of the last couple of 100 years. So you can see this exponentially increasing CO2. Now, interestingly, on the right-hand side, we can see the equivalent radiative forcing. So what does that mean, do you think, the radiative forcing? Because I've mentioned it once, but I haven't clearly explained what that term actually means. So the radiative forcing, and you'll hear this terminology a lot, is essentially saying if we have an equilibrium, and this component balances these two. Okay. If it doesn't, what actually happens? Say, for example, we increase the amount of carbon dioxide. This outgoing long-wave radiation, what happens? It goes down, yes? We've already discussed this. So if we increase carbon dioxide, the emissivity of the atmosphere increases, and the outgoing long-wave radiation goes down. So we no longer have a balance. Okay. Now that imbalance, this instantaneous imbalance, say for example we were just to assume that tomorrow all of a sudden we doubled carbon dioxide. It's an instantaneous switch. Immediately we double carbon dioxide, we have an imbalance in the fluxes. Okay. That imbalance we can call the radiative forcing of that change. So we double carbon dioxide. What is the effect it has on this balance? Okay. And that's its net radiative forcing. Or we can talk about just its impact just in the long wave, and we can say that's its long wave radiative forcing. In other words, just in those long wavelength frequencies. Okay. So that is what we define by radiative forcing. It's not to say that that imbalance would last forever and stay invariant. Why is that? So say tomorrow I double carbon dioxide. The imbalance is 4 watts per meter squared. So the outgoing long wave radiation reduces by 4 watts per meter squared. It doesn't stay 4 watts per meter squared forever. Why? What happens next? Hang on a second. One at a time, please. Sorry. But you do have to shout. Sorry. No, don't make life complicated. What actually happens? What's the main effect that happens after I increase carbon dioxide? So forget about all the feedbacks first of all. What's the primary effect of increasing the carbon dioxide? Temperature increases. Exactly. So when you're answering these questions, think about the main thing first, and then afterwards, if I ask about the feedback, try and keep life simple when you think about this. The main effect. So we had a balance before. We perturb that balance. We have more energy coming in than going out. So what happens? The energy doesn't just go away, so it leads to an increase in the temperature. What happens then when the temperature increases? What's happening to this component here? Careful. So we've increased the carbon dioxide. The outgoing long-wave radiation has gone down, so we have an imbalance. As a result, over a period of time, the surface temperature will increase. What happens then to the outgoing long-wave radiation? No, the question was, what happens to the outgoing long-wave radiation? So remember, stay precise. This is normally examined, this course component, orally. And normally, for the other course, I always do written exams. For this course, I give an oral exam. Okay, well, this should really be off camera now. It's like, cut. But I give oral exams, okay? And so first thing is not to get nervous with oral exams. But the second thing is think about the question and concentrate on that question. So when you have an oral exam, this is just like a little bit of pepping now, what we're not looking for is a brain dump of everything you've ever read in the notes. Okay? We don't want to know when someone asks you a question in an oral exam or any kind of exam, and this is important because at the end of the day, these exams are just a stepping stone. But if you then become scientists in the future, you give a talk at a conference. You have 12 minutes to give a talk. Afterwards, there's maybe 1 or 2 questions. Okay? If someone asks you a question after your scientific talk, you've maybe got 30 seconds to get your message across and answer that question. If you then start giving a brain dump about, oh yeah, I remember reading about something else on page 19, then you're not answering the question and you're not dealing with it in an effective manner. So if I say, what happens to the outgoing long-wave radiation when the surface temperature? Then you have to think, okay, there's only like basically 3 answers. It can go up, it can go down, or it can stay the same. And then you can explain why. So does it go up or down, or does it stay the same, the infrared? Goes up, yes, because we're increasing the temperature. Sigma T to the 4th. We know that as we increase the temperature, it goes up. Okay, and it goes up until we re-establish an equilibrium, you see. Because the initial perturbation reduces the outgoing long-wave radiation. That means we have an imbalance, more energy coming in than going out. That leads to the temperature increasing. The temperature increase is increasing the outgoing long-wave radiation, and it will keep increasing until we re-establish a new balance with a higher surface temperature. Okay, and then we no longer have an imbalance. So the carbon dioxide increase is still there, but it hasn't got should we say, a perturbation effect because we've come back to an equilibrium. So if you see a graph like this, and I should finish now because I've run over, but if you see a graph like this, on the right-hand side, when it says radiative forcing, now you understand what that means. What it means is, given this change, what would be its instantaneous impact on the imbalance of the radiation at the top of the atmosphere? But it doesn't mean that the imbalance has that value now, necessarily, because there's also been some adjustment already in temperature. Okay. So it's the hypothetical equivalent perturbation to an equilibrium system at the top of the atmosphere. I shall finish there. Thank you very much.